Okay, so here's another example we're going to take a look at, except for this time a planet orbiting a sun. So our Earth orbits around the sun. Let's find the following: the time for one revolution in seconds, the velocity of the Earth, and the mass of the sun. We know that there's always this force due to gravity that's pulling our Earth towards our sun. So if we're looking for A, the time for one revolution, we know that the Earth revolves around the sun one time per year. So we know the time it takes is going to be 365.25 days, but we're going to have to convert that into seconds. So we'll notice that our years cancel. We know there's 24 hours in a day. We know there's 60 minutes in an hour and 60 seconds in a minute. If we multiply 365.25 times 24 times 60 times 60, we're left with 31,557,600 seconds. In scientific notation, that's 3.16 times 10 to the 7th seconds. If we're looking for the velocity of Earth, we know the velocity equation is distance over time. We know the distance that the Earth takes to rotate is 2 pi r, so one revolution is 2 pi r over time. And r is the distance between the center of the sun and the center of Earth. So the distance between the center of sun and the center of the Earth is 1.5 times 10 to the 11 meters. And that's another quantity that's given in that table in your textbook. I think they call it the mean distance between the sun and the Earth. So 1.5 times 10 to the 11, plug in our time we calculated earlier, we get 29,825 meters per second. Now if we're looking for the mass of the sun, this is where our forces is going to come into play. We know the force due to gravity is the centripetal force, so it's going to equal m times acceleration centripetal. Plug in our equation for force of gravity, g, mass of Earth, mass of the sun, over r squared. Remember, we can't use the force of gravity as mg because it's not at the surface of the sun. Our Earth is not at the surface of the sun. It's a significant distance away. When we look at that equation, we'll notice mass of Earth cancels. We're left with g times mass of the sun divided by r squared equals v squared over r. Another thing cancels. R cancels, one of them. On the left-hand side, we're left with g times mass of the sun over r equals v squared. We're looking for m of the sun. So m of the sun, we need to do a little bit of algebra. We're left with v squared r over our gravitational constant. Plug in our values for velocity and radius and the gravitational constant. And with a lot of manipulation of the units, we're left with 2 times 10 to the 30th kilograms. I'll let you go ahead and take a look at this unit analysis on your own this time, knowing that our gravitational constant is Newton times meter squared divided by kilogram squared. You will get kilograms left over. Prove it to yourself.